Welcome, grade 12 physics, section 3 on graphs of motion. What am I going to do now? I'm going to do an example. It's quite a long example. It wouldn't be a question because, it might be, but it takes quite a while to get through it. But let's have a look. This is objects passing each other, all right? It's a very nice question that they can give. They have told us that we have got over here. Let me go back to my standard thingy, and over here we have got a building 50 meters high. And what do? I take object A over here and I drop it from the top. And I take object B over here and I launch it upwards at 30 meters per second. Okay. Now obviously at some point these two are going to pass each other, aren't they? So let's just put that in, and over here, I don't know, just so that I've got space, I'm putting it in at that point. This one is going to go up like this, isn't it? We don't know how high at this stage. This one is going to come down like that, correct? So this guy is falling down like so. This guy is going to go up, and he's going to at some stage turn and come back. All right? Now, they say to us over here, objects are passing, they are released at the same time. Calculate the time at which they pass and the distance that object A has fallen. Okay? Right. So what they want to know is that when will they pass? Right? Just think about it. If you start the stopwatch, bim, the time the one goes up and the time they go down, when they pass, the stopwatch, you click, you're going to read the same time. So the objects pass at the same time. Okay? So pass after same time elapsed. Correct? They pass after at the same time as elapsed. What is that saying? Well, let's just split it into our old way, shall we? And let's just see. I'm going to split it here into the down motion and the up motion. So let me just start over here with down. Down, I can say delta x is equal to, say, x1, all right? Or delta x, x1 or x of a, it doesn't matter. It's the down motion. I'm going to call it here x1 is equal to 0 t plus a half times 9.8 t squared, right? Why 0t? Because v initial is 0. I dropped it, okay? They could have thrown it. Then I just put in a velocity initial, don't I? So I say, okay, and a half, and acceleration is positive. Why? Down motion, a positive. So that is going to be equal to 4.9 t squared. Correct? Now let's look at the up motion. Okay? The up motion, delta x is equal to, I'm going to say x2 is equal to 30 minus, 30 is t, sorry, v initial is equal to 30, and it's positive. Okay? I threw it up. Therefore, minus 4.9 t squared, that's a half of 9.8. Negative, because a is minus 9.8 meters per second squared, because if it's going up, I must have a minus a. Therefore, x2 comes out to be equal to 30t minus 4.9 t squared. 4.9 t squared. Correct? All right, now the last thing, but x1 plus x2 must be equal to 50. Therefore, I can now rearrange this, can't I? I can say that x2 must be equal to 50 minus x1. Right? Because let's just go back to our graph here. At this point over here, let me just change color here to a blue. This was x1. This was x2. This is down. This is up. And x1 plus x2, can you see x1 plus x2 must be 50. So I can rearrange my equation. All right? Like so. What is the next step? Okay. The next step is then to substitute in. All right. And then I can say that I can just basically put the x2, the x1s in there, right? But essentially, what can I say? I say the time is the same. So let's have a look here. Therefore, x2 is 50 minus x1 is equal to 30t minus 4.9t squared. Correct? Therefore, after a bit of thing, minus x1 is equal to 30t minus 4.9t squared minus 50. Correct? And x1 is going to be equal to minus 30t plus 4.9t squared plus 50. Right? And x1, have a look here. Let's go to my red. x1, can you see what I've done? It's basically solving simultaneous equations, isn't it? Therefore, 4.9t squared is equal to minus 30t plus 4.9t squared plus 50. And I can rearrange that. Can you see that's going to cancel out? And I get that minus 30t is equal to minus 50. T is therefore equal to 1.67 seconds. I know it's 1.666, but it's 1.67 seconds. Right? Then I can say, okie dokie, if that's the case, now I can go back, just turn myself over here so that I can use the calculations. Now let's back subs. Therefore, okay, therefore, whoa, just go back. Therefore, back substitute. Back subs, the t equals 1.67. Therefore, and I get x1 equal to 4.9 times 1.667 squared, which is going to be equal to 13.62. Okay, 13.62 meters. So I know how far it's gone down. Therefore, x2 must be equal to 50 minus 13.62. Okay, and yours truly didn't switch his timer on, so that I can just minus 13.62, which is going to be equal to 36.39 meters. Right? 36.39 meters. Straightforward. Yep. And let's have a look. Those two add up to that. I could also have said, I could have back substituted delta x equal to 30 times 1.667 minus a half, 9.8 times 1.667 squared. I could have substituted into there, and I get 50.01 minus 13.62 is going to produce 36.39. Okay, same answer. So if I'd have substituted the one into the other equation, delta x, that would of course be x2, right? x2. Okay. Now, let's have a look at a slightly different one. Okay. I'm going to use the graphs of motion where we do this. I'm going to give us the graphs of motion. Let me just get a clean page back onto my thingy. Okay, say we are given the VT graph as follows. We are given a VT graph like this. All right. Right, my VT graph, V is plus, minus V, and time. And what they've given me is they've given me over here 30 meters per second, and just let me just do that like so. And over here, that is this is object B and object A, and they give me one like this for object A, like so. Right, then they tell us, okay, the balls pass at 1.667 seconds. They tell us at 1.667 seconds the balls pass, right? Okay, now use the graph to find VA and VB. Oh my goodness, right? How do we do this? Okay, they want to know at that point, okay, this is VB and this is VA. Okay, they want to know what is the velocity at that point, right? Right, well, what did I say? You always go and put in what you know. This is 0.0 time V initial is 0, all right? You see that? I'm looking at A here, right? Okay, so now I can say, okay, well, right, for A, I know that, hang on, wait a bit. I know here that VA is there, so this VA is my velocity, final velocity at that time. And I know the slope of the line, right? Because they tell us that it is under gravity, or it was two objects falling under gravity, all right? So what do I say? I say, okay, therefore, the slope of the line, the slope is equal to minus 9.8 meters per second squared. It must be G. So for A, I can then say VA minus 0, right? Final minus initial, over 1.667 is equal to minus 9.8. Therefore, VA is equal to minus 16.33 meters per second. All right? How did I get that? I can also say VF is equal to VI plus whatever, right? Okay. Now, so therefore we know that velocity there, don't we? The next step is to say, well, let's have a look now. Okay. VB minus 30, right? Because, hold on, what do I know about this one? Okay. All right. VB minus 30. So I can now go and I can say, right, let me just take this back. Oh, just a second. Okay. I can now go back and I can say, right, VB minus 30. Okay, because that's V final minus V initial over 1.667. That is delta V over delta T must be equal to, correct? And therefore, I can now work out that VB is going to be equal to 13.66. Okay, 13.66 meters per second. It has slowed down. Correct? It has slowed down. Remember, it started at 30, V final, V initial over that, minus, and it's minus 9.8 because it is slowing it down, right? Okay. Therefore, find the distances traveled by A and B when they pass using the graph. In other words, they want to know, let me just go back up a second here. Just let me get to my graph. They want to know the distances. In other words, the same as that graph, correct? So let's just go back to this one. Okay. How do I find the distance on a VT graph? What do I do? It is the area under the curve, isn't it? So we're going to look at the area under the VT graph, right? Remember, I've got that. Now I put in VB, just a second. I'm just going to go and put in my answers in green. VB, I found, was 13.66 meters per second. And VA, sorry, let me turn it, 16.33. 16.33 minus, okay. Now, let's have a look. Okay, let me have a look here. We say, right. You just put my thingy on. You can see I'm just going to use the area under the triangles. Now, when I do this, you just look back at yours. Okay, so therefore, the area is equal to, a half times base times height. 1.667 is the time times 16.33. Okay, let's leave it as a minus. This is going to be minus 13.61 meters. Okay, that is the one. That is B. There, sorry, that's A. And B, area, is going to be equal to, from the graph, a trapezium, which is 30 plus 13.66 over 2 times 1.667, which is going to be equal to 36.39 meters, correct? 36.39 meters, and that is up. All right? The signs, don't worry. Just go back to the actual example and look for yourself. So far, we're going great guns on this thing. We now know 36.39 up and 13.61 down is negative, right? Then they say, at what time does object B reach the turning point? Okay. What? You see the question? At what time does object B reach the turning point? So object B at turning point. Hint, at the turning point, BF must be equal to 0. Okay? Using the graph, okay, it's when VB equals 0. Okay? I've got to keep going back to my graph, okay? So it's the time when VB is equal to 0. Let me just go back here. All right, blue. It's when VB is equal to 0 is the turning point, isn't it? All right, cool. So what do we say? We say, okay, using the graph, okay? We use the gradient again, right? Now we need to just go back. Can you see the gradient? Just let me get back to mine. Whoop. Right, I'm going to use the gradient of graph. Just want to make 100%. The gradient of graph B, correct? I know, here, let me just sketch it out here. Just a sec. Okay. I know that that's 30. I know that that was 1.667. All right. And I know that that there is 0. But hold on. I know that 0 minus 30 over delta t must be equal to minus 9.8, don't I? Okay. See that? So therefore, I can work out delta t is equal to, and it comes out as 3.06 seconds, right? You could also have said VF is VI plus AT. I could have said VF is equal to VI plus AT. Remember, this is just an object thrown up, okay, at 30. So VF 0 is equal to 30 minus 9.8 t. Therefore, t is going to be minus 30 over minus 9.8, which is going to be equal to 3.06 seconds. We've used the gradient. This is V final. This is V initial. VF minus that over this piece here. This is delta t. VF minus that, because I know that m is equal to minus 9.8 meters per second squared. Y, repeat myself, which is fine, dv by dt, delta v over delta t, is equal to acceleration, which is equal to g on Earth, 9.81 meters per second squared. Okay, cool. Now they say, just draw a displacement versus time graph. Okay, right, now, hang on, how do we do that? How do we do that? We say, whoa, okay, displacement time graph, okay. What you do is you start off, okay, we've got our axes here. Let me just make sure, yes, I am. Okay, like that, just put in a line over there, like so and like so. And now they want a delta x, delta t graph, right? What do? Okay, I say, first of all right, the displacement of this ball, this object, at time 0 is 50 meters above the ground. Okay, it's 50 meters above the ground. Right, now, how long does it take to fall 50 meters? I work that out, okay, and I say basically, let me just go up a bit, okay. So I'm now doing how long to fall the 50 meters. So this is object under free fall. So we say, right, falling 50 meters, right? I say, therefore, 50 is equal to 0t, initial velocity, plus 4.9 t squared. Therefore, time is going to be 3.19 seconds. So now I know on my graph that this ball is at 3.19 seconds. Come on. At 3.19. Oh, wait, that's a horrible thingy. I think I've said before, writing on here is pretty. 3.19 seconds is over there, right? And now how do I do it? Oh, hang on. It's falling. So it's under gravity, which means it's a, I know this is not a great one, okay? But it's accelerating under gravity, so it's a parabolic curve. Then I say, right, that gives me that point, right? Then obviously it hits the deck and bounces. This guy, all right, the other one, what does he do? Well, let's look at him. Well, where did he start? And when did it get to the top? It got to the top at, we say, right, you do this, right? Why? Because it's slowing down under gravity. This guy here, I calculated at 3.06 seconds was its height, and we said that its maximum height, I don't think I worked it out here, but the height that it got to, I worked it out on the previous one, 36 or something. Okay. 36 point, we just be sure, 36.39. Okay. 36.39 is there after so much, and then this one continued, and this is going to be at 6.12 seconds. How did I know that? This is symmetrical. It's symmetrical, isn't it? I'm sorry about it. It keeps, my screen rotation. Okay, all right. So we say okie dokie, there we go. Right, it's symmetrical, therefore 6.12, and there is our delta x, delta t graph, correct? The last thing that they want, what height did ball B reach? Okay, 30, sorry, that's 45, my bad. Okay, what height did it reach? Was going to be a 45 meters, I think. Let me just don't look at my previous. At what height did ball B reach? I'm just going to go back over here. Come on. Back to that. Ball B. Sorry, I just looked at the previous one. Ball B. Okay. Oh, that 36 was where they passed. That is where they passed. Okay. Right. So we say, okay, ball B is going to be equal to maximum height. Okay, is going to be equal to what? We're going to say delta x. Sorry about that, guys. My bad. Is going to be VIT plus a half AT squared. And delta x is then going to be equal to VI is 30. And the time was 3.06. Plus a half times minus 9.8. Because it's going up times 3.06 squared. Therefore, my delta 45.92 meters. Okay, so 45.92. Okay, that's going to be there. Let me just put that in red. 45.92. All right, and then when the distance, when they pass, is at the same time. Can you see it? Let me put it in blue. Okay, over there. Right. That is the point where, at that time. Now, that's when they've gone the same displacement, right? Okay. Then the last one is they say draw an acceleration time graph. Okay. It's pretty obvious, isn't it? It's going to just be minus 9.8 and plus 9.8. The plus 9.8 is on the one that's dropping. The minus 9.8 is on the one that is decelerating. Okay. That brings us to the end of graphs of motion. Okay. I hope that you went through those with me. I hope I didn't go too quickly through it. But do try a few. Start with a few easy ones. You know, in the textbooks, there's some easy ones. Just go through the method that I've tried to show you. Put in what you know. Look carefully at what graph you're dealing with. And then split it into the time bits. Always remembering that when something is falling, the slope of a VT is that. The slope of a displacement time graph is your velocity. Okay. And slope of acceleration is neither here. So we've got constant acceleration. Okay, positive and negative. Right. Thanks for watching. Appreciate it. We'll be back and we'll carry on with the next chapter, which is the work energy theorem. It's quite a long one and probably one of the heaviest ones. I'm going to try and make it simple because that's the philosophy of what we do here in the classroom. Okay, I'll see you guys again. Cheers. Bye.